Kevin, you can mention that those are not able to join, they can join, they can watch live on the YouTube, and then we will sort out the issue a little later. So, okay, I think we can start now. Okay, so last class what we have mentioned or discussed is about the how the digital storage of it, especially the numbers, right? How the floating point numbers are stored, what is the round off error, how it is propagating when it is introduced, and also we have seen a little bit about the different precisions, right? When you store it in the 8-bit to 32 or double precision of 64-bit, right? So what's the capacity, what's the range one can store? So today what we are going to see about is today we will be seeing about the little bit of basics of the computer architectures, right? Why do we really need to know? Of course, we are not going to build any computers, and also we are not going to work on the computer architectures. But at the same time, what we really need is, especially when you want to do the computations, you should know at least how to optimize it, right? When you say it's optimize, you have to run the program very fast, in the sense. With a minimal time you should be able to do more work, right? So that's the objective. And then if you look at the how to do that, there are several factors involved, and especially when you're talking about the computational thinking or computational science, of course you have to do a lot, in the sense, one has to not only write the algorithm in an efficient way, but also you have to understand whether your algorithm is capable of supplying enough, or it should not be data hungry, right? When it says the algorithm is data hungry, then what happens is the processor might not be able to do more operations, more floating point operations, because the processor might not get the data. So for example, if you want to get the data, for example, certain computations, you cannot avoid the calculations, you cannot avoid the data dependency, right? Everything is data. Only question is how you are going to judiciously using the data and judiciously utilizing your memory, right? So that's the performance comes into there. It's not only about just buying a fastest processor or a high-end machine, right? You are not going to get. And at the same time, just writing the algorithm in an efficient way, that you're doing a less number of floating point operations, that is not going to work. You have to reduce the frequent use of non-contiguous data, right? We will be seeing when we start writing the algorithms in later part, right? So whenever you do some calculations, you should always try to do some calculations and or the next calculation in a contiguous data, right? So we will be seeing why it is necessary, and then how it is going to affect the performance and other things. So today what we are seeing is just like a basic understanding, right? If you're a computer science student, definitely you must have studied, right, computer architecture and so on. But if you have not done, if you're coming from the different background, at least a very basic thing you should know. Okay, these are the memory types and this is how the memory is connected. So we have to write an algorithm, or when you do some operations, I have to keep all these things in mind, right? That's the purpose of today's lecture. So before starting, right, I just want you to ask simple question, right? I have just launched a poll, right, about your background, right, in the sense of what is your computing knowledge, right? Whether you have already done some programming and so on, if yes or no, and if you're done already, what is the level of your programming, right? Whether you're an expert or you're just a beginner or never done, right? And the question is, have you already studied the machine learning and AI? These are the things I just want to know, because the level what I am planning to do, like the phase of the course, can be planned accordingly.
Still,
Yes.
there's static noise in background sometimes.
Sorry.
I'm getting a static noise in background.
Okay. Some humming sound or what?
Yes, sir. I think it's for me, or I just want to confirm with you. No, it's not that.
Okay.
The static noise is for me too, but it's actually not that bad, at least for me.
Okay. That could be the laptop. It's because it's live on the YouTube also. That's a load to the laptop might be too much. So I think the I'm seeing already it's the fan is running in the laptop. That could be the reason. Okay, so if you look at okay the data in right, how many have participated? Only 39 out of 47. Uh, Others, can you quickly complete? Okay, so you have done, but if you look at in terms of the percentage, right, above 5 probably like 40%. Okay. Okay, 2 minutes, it's going to over. I'm going to stop the poll. Can you quickly submit? Okay, so that's the level, right? Many of you have already studied the C programming, either C or C++, Python, right? You have done, that's very good, 78%. But if you look at the level of your programming knowledge, right? Of course, it varies, right? So different age groups different, and then very few are really in the advanced level, right? So that's the that we will try to cover it. And in order to do that, the whole question is about the purpose of this lecture is about how to improve, right? In this second part, how to improve and how to make you as a good computational thinking guy rather than just like a programmer and using the programming and so on, right? So that's the whole idea of this class. To start with, right, I'm not like, I don't want to go into the computer design, the architecture design and so on, but I'm a user, right? What are the things I need to know, right? The two things, I would say it's you can call it as a law, but unfortunately it's no longer true, right? Then if it is no longer true, then we cannot say that it is a law, right? In scientific laws, if it is stated, right, it must be true, but it is no longer true. But the two things, right, one as a computer scientist or a computational guy, you should know is the Moore's law and Dennard scaling, right? So if you look at the overall growth of computing, right, the computing power in the last 75 years, right, it has completely changed the scientific community computing, right? So for example, whatever you thought like impossible like 20, 25, 50 years before, right, and now it the computing power, right, the growth in the computing power has made it possible. So what does it mean? It means it means that you will be able to do the computing. Just a second. Okay. So you will be able to do the computation, especially the data science field has emerged. We have already discussed, right? It is emerging. It put it in the computing power has put it the data science into the forefront, right? It is the key reason for the success of AI/ML. So that all these stories we know, right? What are the two things important, right? One is like the capacity, right? The processor chip speed, right? So what Moore's law says is the number of transistors on a chip, right? The number of, because the transistor is the one which is responsible for the speed of the processor, right? It doubles every 2 years. But of course, this was proposed in 1965, and the changed somehow, right? Changed from 1 year to 2 years, right? And when initially proposed, it was just like every year, but later it was converted to changed to 2 years, right? But if you look at the history, right, why I'm saying that this Moore's law is also no longer valid, the reason is it is not doubling as it is proposed. So doubling in the sense we will be seeing the graph also, right? The processor speed is not increasing as we expected. What is the Dennard scaling, right? This is also very important, right? The why it is important, because it says that the power density is constant for a given area of silicon, right? Which means that roughly, right, and put it in the layman's language, right? If we keep on increasing the transistors, right, if you don't increase the silicon size, right, doesn't matter, the power will the consumption will remains the same, which means that how it is happening? Because they're small, the transistor is becoming smaller and smaller, then the power consumption is getting reduced, right? So in that way, right, it remains the same. However, this is also no longer true, especially after 2004, right? It is not the case, and that's where, right, and during this period, right, mid 2000s, right, is the one where is the period where we started to see different type of architectures, right? So what is then if you look at the computer performance, right, what are the main goals, right? What are the components that influences? Of course, the Moore's law and the Dinard scaling, right? Because the Moore's law says that, okay, every 2 years the computer speed doubles, right? If we had followed, right, what does it mean? It means that as a computing guy, I no need to do anything, right? Every 2 years I upgrade my system, right, and then I should be able to speed up my algorithm, or 2 times, or otherwise I reduce the computational time by half, right? Just I don't do anything, no optimization, nothing, right? I don't need to do anything. I just have to upgrade the system 2 years once, then my computing time reduces by half. But that's unfortunately no longer true, right? So we are in a different era now. So that we have seen already, right? Even the parallelization and other things, these are the motivations, right? Why it is and how it is changing. That's and of course the improvement in the computer architecture, right, is necessary for the performance, but the improvement in terms of the speed or in terms of the number of processor, these are the things one has to take into consideration. And the third component, right, third component is about the computational algorithms, right? So you cannot just use the old algorithms or the inefficient algorithms. If it is already old, in the sense if it is already implemented in an efficient way, of course maybe you have to come up with even more better efficient way, or you have to reduce the floating point operations. If you reduce the floating point operations, obviously the computational cost will reduce. However, in order to do that, right, one has to go back and understand the physics, understand the model, and understand the numerical scheme as well, right? So that is also very important. So looking at all these things, right, put together, right, computing, right, in a very efficient way, especially in the today's computer, is not so simple as it was like 20 years back or 15 years back. The reason why I'm saying it is not simple, because 15-20 years back you have only one system, or this parallel computer, altogether a different story. We are not going there. Even I'm talking about the desktop system, or the cluster, or the workstation that you are using in your lab. So that has a different meaning, different setup nowadays, and then one has to understand the components, each and every components associated with it. So this is the one graph. I would say that maybe we will go little bit over the history. I will zoom here. So somewhere, right, the technology has driven the growth of the computing. For example, from 1978, so around 1986, right, it's all about technology driven, right? And then the RISC technology come again. If you look at the processors, right, you start with 5 megahertz, right, starting with a 5 megahertz processor, and then growing to 22 megahertz, right, 16.7 different sun microchip, right? And then you can see that IBM 30 megahertz. We are talking about how the growth, right? We are talking at gigahertz. And then if you look at the growth, right, this is how it has gone. But the interesting factor, right, interesting fact one should really look into it, is what is the growth here, right? 52% of the growth. What does it mean? It means that every year almost it gets doubled. We will be seeing that how it is doubled and other thing. But the computing the capacity, the speed, right, it's almost like 52% per year. So it is really getting almost every year, right, and 50% it is increasing. So if you look at here, right, from 1986, I would say this period, right, around 2003 2004, the growth, the speed of the computer, right, the processor speed it's excellent. So we have started from some few megahertz to reached to gigahertz. If you look at here, right, these are all gigahertz size, right, 3.2 gigahertz, right, 2.6. But if you look at 2.6 gigahertz, 3.2 gigahertz, and 2.9, right, somewhere around settled around 3. But if you want to go beyond 3, especially the post 2014, if you look at these years, right, from 2004, even you can say the present years, the compute capacity, right, of individual processor, single, I'm talking about only the single chip, right, this single processor is not increased as expected, right. So we have reached around 3.2 in 2004. What we are talking about is probably like a 4.2 4.2 processors. We are talking only about the desktop processor, not in the workstations, not in the parallel supercomputers, right. So now you see that in the last almost like a 10 years, right, maybe like 8 years, almost no growth, I would say. It's growing, increasing, the computing power is increasing, but negligible capacity, right. So overall, if you look at, right, this is the interesting factor. If you look at why I'm saying that we got enormous computing power from 1978 to 2018, right. Of course, still here the data is shown for until 2018. So if you look at the computing power, right, how much it has increased from here, if you look at it, has increased like a 50,000 times the computing. So for example, what does it mean? It means that if you're doing some computations, right, if you're, it takes like a 50,000 seconds to compute, and today's computer, if you do it the performance, same thing, you can do it in 1 second, right. So that's how the computing technology has increased or improved. But the problem started from here. Why the problem started here? The computing power, that means the number of transistor in a transistor is not doubling every year. Moore's law stopped here. And not only that, and they're not scaling, right. By keep on increasing the compute power, what happens is it started consuming more. It's no longer like we have the restriction on the size, right. You cannot go beyond the transistor size, and you cannot go beyond that level. Then it started to increase the power consumption. When the power consumption got increased, of course, the main problem is it's a conservation of energy, right. When the conservation of energy principle, you have to go to the physics and then come back, right. When the conservation of energy comes into the play, when you consume more power, and what happens is you are going to generate too much of heat, and the heat is also, then the cooling system, everything started failing or needs more and more upgrade. When you want to increase the cooling system, it's indirectly, in addition to the processor, it also started consuming more power. Then when you talk about, when you design a desktop computer and other thing, the first thing you have to think about is the SMB, right. The how much that SMB usually, like if you look at in this era, right, even 90s and 70s, 250 watts, right, or even the 350 watts, I think it's a maximum. But nowadays, if you attach any GPU card, any very basic end GPU cards, then 250 350 watts SMPs are not enough. What you really need is probably you have to go to the 650 750, depends on the card that you are adding. So it's not only about the power consumption of the processor. In order to support the power consumption, right, increased requirement of the processors, then the cooling system is also a lot of complication arise. So that's where this era is a bit complex period. And what it doesn't mean that, okay, this is that's how the invention also comes, right. And then people started to think, the computer experts, right, the architects started to think that, okay, how to manage this, right, because now we have reached certain level, then we are not able to do. But if you are trying to push, then we are going to get hard, especially in the power consumptions, cooling, all the complications comes. That's where the idea comes about the multi-cores. Instead of just increasing the speed on in just one processor, why don't you add two processors, right, three processor? That's where the idea comes, like quad core, right, dual core. Started with dual core, quad core. Now you imagine, right, the chip motherboard, right, it can have like a 6432, and even when you go to the AMD, you can also go beyond 100 cores in a board, which means that of course it put some restriction, but it introduces new possibilities, right. When you talk about the new possibilities, of course, then one has to think about how to design the algorithms. Now it's a completely different architecture, right. So far up to here, right, around 2000s, in the beginning early 2000s, we were thinking about like algorithms. I'm not talking about the parallel algorithm at all, even the sequential algorithm itself, right. We were talking about how to efficiently write efficient reduce floating point operation, that's enough. But beyond this period, now I don't think nowadays any even the workshop systems, right, even you can really started with dual cores, right, and you can really see that, okay, here and all you can really show that it's nowadays i7 processor and 16 cores and other things is very common. Okay, so now if this is the case, then definitely we have to think about how to utilize these type of different architectures in an efficient way. Just to give a brief overview of the growth and performance, right? So if you look at till mid 80s, right, it's mainly technology driven, right, and then it's doubles, the speed doubles every 3.5 years. But if you look at the, I would say it's the golden era for in single chip, single architecture, because it's okay, so doubles, it's not 8, it's a typo, so doubles every 2 years during this period, right, starting in 1986 till around 2004, it doubles every 2 years. But what happens is after, right, after 2004 to 2011, during this period, its speed got decreased. This we have seen 3 to 5 years it took to double, and of course end of Dinard scaling. And this is the period, right, which forced to rethink about the architecture. In fact, if you go back and look at the Intel's history, right, they have in fact they have started some project to accelerate the speed, but they were forced to close, stop that project and relook into or redesign in such a way that okay, they should concentrate on the multi-core, right? So this is how the multi-core idea came, and it is not like by choice, right? We are, it is by forcefully done, right? We don't have any option, but we are forced to come up with this choice. So this is the period I mentioned, right? The speed has stopped increasing, almost stopped every 8 years, doubling, right? It's almost nothing, right? So we have to wait for 8 years, and then I'm sure that it will stagnate. It won't increase beyond 4 gigahertz, right? So now it's around 4. Some turbo and other things, that means beyond the clock speed, they are pushing beyond their limit, right? Maybe the 10% of the clock speed is increased. Intel come up with ideas like a turbo boost, right? So turbo boost, like beyond the clock speed, right, you are accelerating, pushing the processor beyond that. Maybe only for a short period of time you can run on the turbo boost level for longer time, right? That we are not going to get involved, but you should aware of that. This is how. But I would say the maximum 4 gigahertz, that too for the desktop processor. If you look at the workstations, if you look at the clusters, probably it will be around 2.5 to 3 gigahertz. You may not go with, you may not get beyond that speed, right? And I'm talking about the individual processor. Okay, so this is another classical example, right? So here you can see, of course, this is also some reference, you can see it, everything is taken from here. So here is the case, right? The number of cores, right? So up to like 2004, it is single core. You can see it is 10 to the power 0. That's basically like we are talking about the single processor. So here, this is the period, right? You can really see that the number of cores, it started increasing. Of course, it is not like exponentially growing, but it's almost like stopped. So here itself, you can really see that it's a 64. But if you look at the if you update, right, this is of course the old picture. If you go to the 2020 2021, AMD has come to up to close to this dot. You can find some dots over here, right? So it is growing, right? The number of cores per system is growing. But if you look at the power consumption, initially you can really see that the growth, right? This is because of the increase in the compute capacity, right? Single processor, but the speed got increased from megahertz to gigahertz. The power consumption is also more. But after introducing the clusters, this is a very interesting picture, right? So after introducing the multi-core CPUs, then you can see that the power consumption remains almost, right? I'm not saying the constant, but at least the curve is getting flattened. This is really a good news. And then the same trick, frequency also, right? Up to here, you see that the frequency is increasing. That means the processor speed is increasing over this period. And then post 2004, you can see that the processor frequency is more or less, it's almost in the scale. And similarly, single thread performance, of course, it must be the case relevant to this one. And then the transistors, right? The number of transistors in a chip, in the silicon, right? You can really see that it's still increasing, especially during this period also it's got increased, but not in terms of like in a single processor, in terms of the multiple processor. So this is the overall history of how we ended up with the multi-core And once if you understood the concept, right, we have no choice. One would have argued, right, why you are thinking about like a why should I do the parallel computation, why should I worry about the OpenMP, right, shared memory machines, because multi-core I have no other option, I have to do it. But the problem is it is not by choice, right, we are forced to do that, we have to do it. That's the reason I told, right, if you want to become a computational guy, if you are doing some scientific computing, no other option, at least a basic understanding of parallel programming is needed. Even if I'm not worried about the MPA, right, you should aware of how to handle the multi-core architecture, right, at least this knowledge is the bare minimum. This is like kind of like a knowing a language, right. If you ask like 25 years, like a typewriting is a special set of skill, right. One has to go to the typewriting class and learn certificates, exams, right, shorthand and all these things they do. But after the computer revolution has come, right, so then typing keyboard using it's a day-to-day life, it's not a special skill, it's a default skill. Likewise, what I'm saying is another 10-15 years, parallel computing using at least the shared memory machines with the shared memory implementations like OpenMP is going to be like a default skill for computing guy. So you should acquire this knowledge even if you have not started this, right. So this is what I reiterate, right, way out is only the multi-core. So once we are talking about the multi-core, then no other option, we have to learn the multi-core. Again, the timeline of hardware developments, mainframes, and then mini computers, right, 90s, right, about the different technology, right, and this is the era is started the we have seen that it started the be seeing the multi-core CPUs, and then the thread level parallelism has started, right, and especially the mid to 2010s, right, the GPU computing. So that's basically the NVIDIA has dominated the world, right, in terms of the GPU computing post 2000, around 2010 to 2020. This last 10 years, I would say that when you talk about the GPU, it's mainly about NVIDIA. It has dominated the world too much, especially the GPU computing world. But other AMD is also proposed. AMD also has come up with the this graphic card, right. So one should know about there is no other option. You have to do a lot of computations with the GPUs also nowadays, especially the people working in the data science. No other option. And okay, so this is the another concept, right. We will be seeing that what is data parallelism, different types and so on. And also, right, this is, I would say, it's the current trend. The current trend is about like using low precisions, mixed precisions of floating point operations to accelerate the speed. Right now, you see that evaluation. Right, we started with single core processor, and then till like 25 years, right, almost no progress, just only increase in the speed. Of course, it's a very good speed, but post 2004 it got changed to multi-core, and especially post 2010 GPUs got introduced, and then that is also coming as a very big way, right. So that is the reason why it is not the same as 20 years before. If you started your if you look at the careers of the scientific computing persons, then they might have done something else 20 years before. But if you look at closely now, they need a different skill set, right. It's not only about like coding and programming, it also about knowing the architecture and knowing the algorithm to harness or develop the algorithm in such a way that you can utilize the full capacity of the your new machines, right. That's a summary. The end of exponential growth in single processor performance makes the end of single processor computing. This is the time period is over. In fact, it's over like almost 8 years before. The era of sequential computing must give way to new era of parallel computing. That's the way forward. As I said, it is not by choice. It is we don't have any choice basically, right. It is by forcefully we are for asked to do that. And the next one is the parallel computing is not easy, right. As yesterday's sequential programming, of course, one has to spend some time, understand the architecture and different memory types, right, and then one has to learn and implement. But no alternative exists to improve computing performance, right. If you don't do, then the game is over for the computing performance. So almost all ML packs and tools use multi-core, multiprocessor GPU, TPUs, and that is the reason why if you are like a data science guy, so you have no escape. You have to concentrate more on the parallel computing as well. So if you are not registered for the introduction to scalable computing, you do register, and also if you are registered for that course, then you have to do it very well, right? Try to understand each and every concepts behind the scalable computing course or parallel computers, right? Okay, so now we have seen the brief history about like how the computer the history of computers, how it has progressed, how it has grown, and currently what we are in the era is about the heterogeneous system. It includes a multi-core, it includes even the GPUs and some other accelerators also possible, and in addition to that, so we are also having the possibility of having like mixed, right, multi-node operational, right? Multi-node comes into the picture when you have like more than one set of server, right? It can be connected to the your local area network, or it can be a high speed bandwidth, kind of an infinite band and other thing. Okay, so if you look at the class of computers, you can classify it into 4 categories. The first one is IoT or embedded computers. This will be very small but still very popular. Why? Because it's cheap, of course. Only the 88 or 32-bit processors. It's not like 64-bit processor. 32 is very rare, mostly like 8-bit processor. Why it is important? Because it's like an embedded computers, and then it is used in everyday life. For example, microwave, washing machine, right? Most of the printers, network switches, right? Automobiles. So all these places, right? This embedded computers are already part of it. We call it as a chip, but it's basically the embedded car, right? Even when you take your car vehicle to the service station, right? So they nowadays they don't check, okay, where the problem is, they don't remove it, right? Probably if you are aware of, if you closely monitor, how do they monitor check is just they come and insert connect their device to the system, to the car, right? There is a place you can closely check next time if you are taking your new car for the service, and then immediately then the app gives like, okay, what are the conditions of different components, whether electrical lines, everything is in the right condition or not. All these reports, right, you are going to get it. So that's why the chip is already, the embedded computers are already part of our day-to-day life, but it is not compute intensive as what we are seeing in the desktop or the workstations. So IoT, what it means, Internet of Things. IoT, what does it refer? It refers again the embedded computer, but that are really connected to the internet. So what does it mean? It means that you no need to take the car to the workstation, right, workshop. So instead of taking the car to the workshop, if it is connected to the Wi-Fi, then the company might be knowing, right? They can have maintain a big database, but all these things, and they can monitor, okay, this car has now it's the mileage is of 5,000 kilometers over, then it's in time for service, and then we are this part is one of this much, and then probably one has to do the replacement, all these things, right? Everything day to day. The simplest example is even we have started to use it, right? Alexa, right, or any other smartwatch, smart. If you add, everything comes into under the category of IoT, Internet of Things, right? Because the embedded computer is connected with the network, and that system provides the feedback, right? The data returns to the main server, and the main server takes the data and do some operations, and it says either to operate it in different way, or it conveys some message. It's up to us. The simplest example is like smartwatch, right? Smart home, smart speakers, smart cars, smart cities. Of course, everything is Wi-Fi connected. Then it's everything on your palm basically. So this is also having a big market, right? Even it was estimated that in 2020 that will be around 20 to 50 billion devices will be used. You can, if this is the case, right, you can really the importance of the embedded computers. But of course, when we talk about the computational scientific computing, we don't talk about the embedded computing, right? Because that is not the focus. We are talking about solving something. But before going there, right, there is one more category also, right? Personal mobile devices, PMDs, right? It's similar to the desktop. Earlier it was not there, but nowadays, right, if you take the tab, it's very difficult to, for example, iPad. If you buy this iPad 12.9 or this latest iPad, it's very difficult to classify whether it is a laptop or is it a device, right? Because it is having almost same, right? Sometimes it is better than several other laptops capacity also, right? So it's almost more or less it's become, even if you take a smartphone, tell me one smartphone, right? I'm talking about the high-end smartphones that is coming with single core processor. It's a dual core, right? Minimum is a dual core, but a quad core, arc core is the minimum configuration of the very decent smartphones, which means that it's no longer the personal mobile device is though kind of an embedded, but it is in between the embedded computer and the desktop computer or the laptop type, right? Because it is the gap is very very narrow, and then it's a lot of gray scale. So you can say that it can climb this one also like a desktop computer, or you can climb that as a personal mobile device. Okay, again, that is not the focus, but maybe in future, right, it might come, right? Okay, you might be for example, if you are like an app developer, obviously, right, you don't have an option, you have to develop an app which is running efficiently on the personal devices. But the focus of this course is not first two categories. The focus is about the second. Okay, here it's of course the servers, the four. So what is the focus of this course, or the idea what we are planning to do, looking into, is like the servers and the desktops. So if you look at the desktop computing, of course, it is the largest market. Why I'm saying, because almost everyone buys, right? It's the largest market in terms of sale. But what is reported is the sales are declining. So which means that probably people are switching to the personal mobile device. I would say that this is the one, the culprit, it taking the market, right? For example, nowadays, instead of buying a desktop computer, I prefer to go with like the high-end laptop type, so that I can use it in both ways, right? So that's the reason. But still, desktop is the largest one. So most important, when you talk about the scientific computing, the most important component is the servers, right? Of course, when you talk about the servers, it's we are not talking about the supercomputer, right? So the supercomputer, the problem is you cannot maintain it, right? If somebody else have to maintain and all these things. The servers, of course, if you are like in the labs, right, you might be having the workstations, right? Those workstations are like servers. What is the difference between the servers and the desktops? It's more, servers are more reliable, and also the computing services, right? It computes precision and other thing, right? Especially we will see it, what is more difference between the server and desktop. It's not only about the reliability, right? Of course, the file system, all the reliability and computing services are needed, and it is also about the memory hierarchy and so on. And of course, it's the backbone of a large scale enterprise computing, right? Almost all labs runs. And when you talk about the servers, it has to run 24/7, but that is not the case with the desktops, right? Designed for efficient throughput. Then we will be seeing that, okay, what's throughput, latency, right, bandwidth, all these things. Probably in the next class we will study about it in detail. I think this is the fifth one, right? So fifth one, I would say that okay, I will correct it later. So the fifth one is about the clusters, right? When you talk about the cluster, it need not be a supercomputer, right? It can also be just like the collection of desktops or collection of servers, right, connected with your local area network LAN, right? That is also like warehouse type computers, right? Especially the Amazon, right? These type of big warehouses, and they are using this type of machine. They don't run the clusters, right? The real supercomputers need not be used, but it is okay to put it the different clusters with local area network, connected with local area network. So each node runs with its own operating system. This is the difference, right? Each node runs with own operating system and communicate using the network protocol. It all depends, right? We have, for a scientific community people, right, what we really need is the fast, right, the efficient network, right, which means that we are talking about the supercomputer. It's when you talk about the local area network, we are talking about the InfiniBand and such type of switches. The reason is maybe 100 gigahertz file transfer is okay, but not enough. Like one has to talk about like the 1 terahertz and other things, right? So it's not about like the regular LAN ports, right? LAN we don't want to use it in a supercomputer. So once if you are coming into this category, the biggest challenge is how to handle the communications and so on. So that's where the problem comes, or at the same time the challenge comes. One has to read about it. Okay, so now we have seen that, okay, different types of computers, right? Once you have the different types of computer, now I want to move on to the implementation part. When I go to the implementation, because ultimate goal is not for us, it's not about the architecture, it's about how we can do computing efficiently. So then I have to check, okay, I have different types of machine, right? We will see it in detail also what are the different types in terms of heterogeneity. But even now, right, we know that okay, there are like a class desktops, and then the workstations, servers, and then the clusters, right? At least these three types of machines we are having. What about the implementations? What about the computations? How can we do? So then one has to think about like how to make use of it now, because we are in the era of multiprocessor, and how to do that, because it's not like a single instruction, single work, single data, right? One job, one time, right? That era has gone. Because we have multiple processor, we should be able to do multiple jobs at the same time, right? How to do? I'm not talking about the parallel, just I'm talking about the one node, right? One server, right? Because the server contains the multiprocessor. So when you talk about the parallelization, right, now you see that even if you are without going into the supercomputer, we are talking about the parallelization. What type of parallelism we can do it, right? The first one is the data level parallelism, which means that there are datas, right, and that can be splitted across the different cores, and these cores can compute independently without worrying about the data of the other component. Can you give one simple example in scientific community where this type of parallelism is used? Some application, some numerical method, somewhere. Can you give one example for DLP, data level parallelism?
The training of data in machine learning course, machine learning type of problems, when we train it on GPUs, the
When
matrix
you
are done parallelly.
Okay, so it is done in parallelly, but when you talk about the machine learning, right, at the end of the day, you have to fine tune the weights in the neural network, right, or other control parameters. If you even when you talk about the regression and other things, right, those coefficients need to be, right, fine tuned. But somehow you need the communication at the end, right? You cannot, like, if you train 10 different if you split the data into 10 groups, and then if you train 10 different models, each model will have the say different coefficients, different weights, right? Somehow you need the communication at the end. But to start with, yes, you can do split the data and do it independently, yeah. But there you need some at the time of at the end time, or maybe during the iteration, you need some synchronization. Any other example? That's a popular, one of the popular methods, right?
A cross product, sir, of two vectors.
Cross product of two vectors. Okay.
So matrix multiplication.
Matrix multiplication. So only like a data. You know, don't you need any communication? I want to split the data and put it in a different processor, and the different processor should be able to do.
Yes, so we can we can split them into different columns, and each processor can calculate the product for each of these columns, and finally add all those columns into one big matrix.
But then, which one you're talking? You're talking about the matrix vector or matrix?
Matrix vector also can be.
Matrix, when you're talking about, right? For example, if the processor 1, right, or the thread 1, we should talk. When it says the processor 1, it means thread. We are not talking about the MPI. So, right. So the first row, first column, right, it should be available in one processor, right? Similarly, first row, if you're, how do you want to split the data? First row, first column, first row, second column, first row, third column, which means that the entire data should be in at least either one of these matrices. One row, if you assign to one processor, if you're having 100 rows, then you can have like 100 processors. That is fine. But the B matrix, right, must be available in all processor. Otherwise, you will not be able to do all the calculations, right? So you think about it, right? The data depends. It's not like a clean split. For example, if you do the dot product, right, of course, I can split and do, but at the end, right, I need this global sum, right? Dot product of two vectors. The simplest example for the data parallelism is the Monte Carlo simulations. When you talk about the Monte Carlo simulations, right, everything is independent. You have the same different sets, right? Each processor can have like separate different initial condition, and each thread can start their computation and run it. It's completely independent. I'm not worried about what the neighboring processor is doing, right? So that's it. You're splitting the data, right? When you're doing the computations, other processor is not depend on this data. Of course, you can have some the matrix multiplication. You can have additional copies on each processor, but that's okay, right? We are talking about the shared memory machines, multi-core machines, because it's not really a additional copy, because the memory, whatever you stored, right, is accessible by from each processor, so it is okay, right? So next is the task level parallelism. When you talk about the task level parallelism, it is not, you are not bifurcating, or if you are not like dividing the data. So what you are trying to do is you are just dividing the tasks and then assigning each task to one processor, right, in the multi-core setting, right? So two types of parallelism is possible, and then the question is, we have to mix match it. It depends on your application, depends on our algorithm. We have to start writing in this way. So for example, using these things, right, then one has to go back and then map it, these type of parallelism with the different architectures that are available in our hand. So for example, instruction level parallelism, right, that is mainly about, right, if you're having a data at the compiling time itself, right, you can split it. And the good example is, for example, if you are using the C++ 17 and so on, right, you can pre-compile, right, pre-compile some of the codes, and then the results might be readily available, provided that you need to have like initial data already at the compilation time, but that's altogether a different story, right? It's mainly about like the exploiting, right? It's exploiting the data parallelism. So if you have like a clean data available for each processor, and even at the compilation time you can do something, right? That's instruction level parallelism. And the next one comes into the vector architectures, right? Again, vector architectures, data parallelism. GPU is one of the example, data science example. You have the data, you split the data, you push it in the GPU. GPU will be doing more and more computations with the same data what you have done it, right? It's basically you are doing the single instruction to a collection of data in parallel, right? We will come about the single instruction, multiple data, all these four categories we will see. And the next one is the thread level parallelism, right? A thread level parallelism is something like you can have like a data also independent, but you can also like a TLP, right? Thread level parallelism comes because the task can also be splitted. It need not be like a single instructions, right? And then the request level parallelism. So here the request level parallelism is the one you can, I would say this in a gray area, you can say that this is a kind of like MPI implementation, right? This is a kind of like MPI, and I would say this is the kind of like OpenMP, right? This is more of a like for the shared memory machine, and this is more of for the distributed memory machine. Of course, here the intervention of the programmers and algorithms, operating systems are needed, the last part, right? So the difficulty level increases when you go from the top to below, right? So here you don't, as a programmer, you no need to do anything. So the compiler will take care. So here, of course, programmer no need to do anything in terms of the implementation, but they have to choose, right, what needs to go to the GPUs, and just like splitting the data, manipulating here and there, right, should be able to do. So from here, right, of course the programmer contribution is started, right? In addition to the architecture, known architecture, one has to know that which part can be split and how many threads has to be used, all these things. But here even more, right, it's not only about the splitting the task, and in addition to that, you have to increase the communication. You have to plan the communication, when to send this information to the neighboring processor, or whether the neighboring processor or the neighboring node depend on this data and other things. The programmer interventions are really more, especially in the last level. That's why that's what I said, right? The difficulty level of programming, right, increases when you go from the top to bottom. That means the involvement of the programmers will increase. Okay, so based on these, right, we have seen about different type of parallelism, task-based parallelism, like data level parallelism, and then the different classification of machines, right? So what in terminology, or what is used in the scientific community or the computer science, is like these four simple classifications. What are these four simple classifications? The first one is like SISD, right? A single instruction, single data, which means we are talking about this single processor, sequential programming. You are saying that, okay, you are submitting a job right? You are asking to do some computation, this is a single call, and in this single call you are passing this data, right? And there is no partition, nothing, right? Everything is done on a single. This is standard sequential computing, right? Through it can be exploited the instruction level parallelism, ILP, right? But this is, as I mentioned, right, this is no longer enough, right? The reason is almost all computers comes with multiple multi-cores. Okay, so this is very interesting one, right? The why it is interesting, because this is where we are talking about the shared memory machines, right? This is where I am talking about the shared memory machine or the multi-core processor. Why? Single instruction, multiple data. Okay, there is a typo. Single instruction, multiple data. So which means you are talking about like the simple calculation is finding the running a for loop, right, for the dot product. When you run the for loop for the dot product, the instruction remains the same. That means the program remains the same. What are you doing? You are just doing, you are passing multiple data, right, for each, when it says a stream, right, or you can say that for each core you are passing a different data, but the instruction, right, is to find the dot product, right? That's a single instruction, multiple data. And then of course for the completeness of two concept, right, it is there, but that means the multiple instructions, single data, it's a very unlikely, right? Why do you want to do so? Because we are talking about the scientific computing. In the scientific computing, what you will get is you are going to get if, unless otherwise you change the data boundary conditions, you will not be able to get different results, right? This is almost null and void case, right? It's of no use. But what is important here is the multiple instruction, multiple data. Of course, each processor has its own instructions and data, and more flexible than is this single instruction, multiple data. The reason is in the MIMD, right? It's not ND. So it's a multiple instruction, multiple data. You can pass that, okay, in this case, okay, each one can have like a different instruction, but this type of machine can also take like, okay, each processor I copy the same instruction, but should be doing the computing with the different data, right? So this is, I would say, that a kind of, again, distributed computing machine. This is like the shared memory machine, not this one. So this one is the shared memory, and this is kind of a distributed memory machine, right? So that's the difference. And mostly like we will be using these two one, this one SIMD and MIMD. These are the two things that we will be keep on using in scientific community, right? So with this I stop here today. If you have any question, you can ask, right? And next class, what you're going to talk about, I'm just going to show the different parallel architecture machines, and then we are going to start about the memory hierarchy, right? What is L1 cache, L2, why it is important, and how the performance is affecting, and other things we will be seeing it. Okay, so here I'm stopping for today, and then if you have any question, you can ask.